Okay, so let's focus this a little bit. Better? Okay. So, related rates problems, we're dealing with rates of change. A rate of change of anything is its derivative. So here are the guidelines. First of all, identify all given quantities and quantities to be determined. Identify all given quantities and quantities to be determined. Make a sketch and label all the quantities. Label, yeah, all the quantities. Okay, step 2. Write an equation involving the variables whose rates of change either are given or to be determined, whose rates of change are known or unknown. Unknown means we're going to figure them out, but we have to put letters to them. This is all directly from your book. Page 450 is exactly where I'm getting these guidelines from, word for word. So, step 3. So basically, I have to read through the problem and I have to pluck out from the problem. I have to get out from the problem all of the numbers that I know, and I have to put a letter with them. I also have to take and put a letter with everything that I'm looking for. Like, if I was looking for the radius, what letter would I put for radius? R. If I was looking for the height, what would I put for height? H. Now we're going to learn some new variables. For example, if they ask for the rate of change of the height, we're going to have to give that a variable. And we don't use, that would be the derivative of H, but we use some different variables. So, step 3, using the chain rule, / implicit differentiation. Using the chain rule and implicit differentiation, find the derivative of both sides of the equation. With respect to time. With respect to time. What letter do you suppose we're going to give time?
T.
Okay. T. And for the last step, after completing step 3, plug in all known quantities, all known values, and solve for the unknown. So these are our guidelines. If you wanted your book out and open so you could refer to them while we're doing examples, that's fine, because I can't leave this up here and do problems. So what I did give you for examples that we're going to look at today is a worksheet. So if you don't have, it says notes 2.6, that's what we're going to look at here. And I'm just going to go through and I'm going to follow those steps on probably 5 of these examples today. And then you're going to have your homework is the next assignment. Page 150. I was looking at the 4 for some reason. I don't know why. I was at the 400s in Calc 2. So, whew. Come on up and get one. I've got it up here. If you want one, come up and get it. It's right there. Okay. So here you go. Here is your assignment. Is going to be number 32. Now, I haven't given you the worksheets. It shouldn't be 2.5. It should be worksheet over 2.6. So I haven't given you the worksheet yet. What you have in front of you is notes, not a worksheet. So I'll give you a separate worksheet, and then this assignment is a review of implicit differentiation. So it's all one assignment though, new and review. All right, so here we go. Here's us solving related rate problems. These are not hard. Okay, the first thing we have to do is read the problem. A spherical balloon is deflated so that its radius decreases at a rate of 4 centimeters per second. At what rate is the volume of the balloon changing when the radius is 3 centimeters? Okay, so the very first thing that I try, basically step 1 says write down everything you know and put a variable to it, and put a variable to what you are trying to find. So I always look for what I'm trying to find first. It says, at what rate is the volume of the balloon changing? So, what quantity am I dealing with that's changing? The volume. So, I'm obviously going to be dealing with a volume equation of a balloon. Now, V, though, this V is not the rate of change. Okay? V just stands for volume. The rate of change of volume, and this is important, so you might want to make sure you're writing the words down. The rate of change of volume is the derivative of V in terms of T. That's what the steps say. When you're finding the derivative, it's always in terms of T. Time. So the derivative of volume in terms of time, the variable that represents the rate of change of volume, is dV over dt. Now, is that something brand new? Not really. Remember, another way to write the derivative of y, other than y prime, isn't it dy over dx? The derivative of y in terms of x. We are always differentiating with respect to time, because all of these things that we are looking at, these related rate problems, are dealing with something happening over time. The balloon deflates over time. Water leaks onto a floor over time. A cube grows over time. It's all in relation to time. So every derivative you take, whatever the variable is, so the derivative of volume is dV over dt. What if I'm dealing with an area? So I'm just real fast going to jump down to number 2 real fast. It says, how fast is the area of the pool changing? So we're dealing with an area there. What is the rate of change of area then? Rate of change of area would be represented by what variable? dA over dt. That is the derivative of area with respect to time. Okay, so that's just a little bit about the variables we'll be dealing with. So now I'm going to go just focus on problem 1. Again, the whole point of this is the first step is I have to take and put every number in here with a variable, and I have to write down what variable do I want to know. So the variable I want to know is at what rate is the volume of the balloon changing. So this is my question mark. That is what I'm trying to find. Rate of change of the volume of the balloon. And then we get another little piece of information that says when the radius is 3. So what would I write down for that pertinent information? What letter goes with radius? R equals 3 centimeters. Okay, don't make it hard. Don't look at me like you don't know how to write R equals 3, because I know you do. It just seems really hard now because we haven't done this. So, okay, now we have to deal with this number, 4 centimeters per second. Now, here's what I can tell about this value and how it's different from this. Well, how are these two values different from each other? Well, this is just a centimeter and this is a centimeter over time. So this has to be a rate of change. This one has to be a rate of change. This has to be a derivative. This is the rate of change of what? Read a few words before it. No, the radius. Okay, so that its radius decreases at a rate of 4 centimeters per second. So what variable would I put with negative 4 centimeters per second? Why did I put negative? And you know what? Actually, it's easier if you don't put negative. Don't put negative, just leave it positive. We can write the word decrease at the end. Okay, so 4 centimeters per second would be what variable? Isn't it the derivative of radius? Isn't it the rate of change of radius? So what would go with that? dr over dt. You'll get it. The rate of change of anything, the rate of change of s, ds over dt. The rate of change of h, dh over dt. It's the derivative, is all it is. Okay, so now, have we taken all the numbers that we have? Did we put a variable with them? Okay, and did we figure out what we need to know? Okay, so now we're on step 2. Write an equation involving the variables whose rates of change either are given or are to be determined. Okay, well this is usually just it's not always, but in this case it's the volume formula of a shape. What shape is this? A sphere. A sphere, it's a ball. So the volume of a ball, a volume of a balloon, volume of a sphere is 4/3 pi r cubed. Okay? I'll give you a formula sheet on the test. All right, all the formulas you need on the board. Okay, you should actually know them. Okay, but this is the volume of a cube, or of a sphere. Okay, so now we've done step 1 and 2. Now it says using the chain rule and implicitly differentiate both sides of the equation with respect to time. So, that sounds hard, but all I do is say, well, what would be the derivative of v? That would be dv over dt. This time, instead of just, when we did implicit differentiation, whenever we took the derivative of y, we took its derivative, then multiplied by y prime. Or you could think of it as dy over dt. Same thing. This time, we just take every variable gets multiplied by dv over dt. If I take the derivative of r, then after I take that derivative, I multiply it by dr over dt. That's what they mean by chain and implicit. So what would be the derivative of 4/3 pi r cubed? Just all by itself. Isn't it power rule? Multiply by 3, so you get 4 pi r to what power? Second, times dr over dt. Since I took the derivative of r, I multiply by, it's like multiplying by r prime. But we write dr over dt because we're always with respect to time here. Okay, so there was step 1. I did step 1 here. I did step 2 here. This is step 3. And now step 4, I'm just going to plug all the values in. So I'm looking for dv over dt. So now I'm on step 4. I'm plugging in what I know. I do not know dv over dt. I do know r. What's r? So 3 squared. And I do know dr over dt is 4. Now I'm going to do you a favor. 3, the label on 3 is centimeters. Okay, so I want to make note of that. And when I put 4 in, the label on 4 is centimeters per second. Okay, and that'll help us figure out what label we need on our answer. Because if without an answer, without a label, your answers are wrong. Okay, so now continuing, just working this out, dv over dt. And when I say you can leave answers in terms of pi, do you understand what that means? So you don't need to multiply by pi, write it as something pi. So 3 squared is what? 9 times 4 times 4. Calculator out. 9 times 4 times 4. No. Should be way faster than this. You should already have a calculator. 144, thank you. So 144 pi. So the rate, this is saying the rate of change, the rate of decrease in volume is 144 pi. Now the labels, if I squared this centimeter, I took centimeters times centimeters, and then I took times centimeters again, what power is the centimeters to? Cubed per second. So the rate of change of the rate of decrease in volume is 144 pi centimeters cubed per second. Cubed is always a label for volume. What's always a label for area? Something squared. Okay, so that is one related rate problem all solved. This is your final answer.